So in this video, we're going to be talking about net ionic equations. So the statement, the objective for this topic is to represent changes in matter with a balanced chemical or net ionic equation. So this is where we're really getting into the essence of how we write what happens in a chemical reaction. So when we write net ionic equations, we are often using them with precipitation reactions. So this is specifically for net ionic. With other types of reactions, we'll write them a little bit differently. It all depends on what you want to show. So we are going to use net ionic when we're talking about precipitation reactions. So a reminder, a precipitation or a precipitate is a reaction that produces a water insoluble product. So that means it's a solid that's not going to dissolve in water. We are specifically looking at aqueous net ionic reactions, so things that will not dissolve in water. They might dissolve in a different solvent, but they're not going to dissolve in water. So the precipitate is the solid that forms. And we can also think about these reactions as exchange, or you might see them referred to as double replacement reactions. So when we look at how the reaction is written, we're talking about ionic compounds here, not molecular, so not covalent. So as a reminder, an ionic compound, an ionic compound is made up of a positive and a negative ion. It can be multiple, it depends on however the charges are going to get balanced. So in this reaction, we have two ionic compounds. Our first one is made up of cation A and anion B. Our second compound is made up of cation C and anion D. So these are just generic formulas. And then they're considered exchange reactions because they basically just switch partners. Okay, A was partnered with B. Now it's going to partner with D. It can't partner with C because two positives aren't going to go together. So remember, ionic compounds are made up of opposite charges. So A is going to go find its other opposite charge. So its two options are B and D. Well, it's already partnered with B, so now it's going to go find the other one, which is D, which leaves C and B to be partnered together. Same idea. So B is a negative charge, so it's going to go find a positive charge. It's already with A, so it's going to go find C. And those give us our reactants. Now, when we go to write net ionic, this is not a net ionic equation. This is just showing how they're moving, why we can call them exchange or double replacement reactions. To write a net ionic, we have to think about what's actually going on. So there's kind of some steps here. And there's three different levels of how we write the reactions. The first is the molecular. So that's what we started with. It shows the complete formulas. So my example here is silver nitrate reacting with potassium chloride. When it switches, so silver is my positive, nitrate's my negative, potassium's my positive, chloride's my negative, so they're going to swap. So silver is going to go find the chlorine, so it's going to make silver chloride, and the potassium's going to go find the nitrate, so it's going to make potassium nitrate. Now, the symbols come from their solubility rules. Okay, so our solubility rules tell us that silver nitrate is aqueous or soluble. That's what AQ means, because nitrates are soluble in water. Potassium chloride is also aqueous, so it's going to dissolve in water because first column and column 17 compounds are generally soluble. Okay, and then we're going to form silver chloride. Now, when we say column 17 compounds are usually soluble, there are some exceptions. Silver is one of those exceptions. So silver chloride, although chlorides are usually soluble, silver chloride is not, so it's a solid, so we put an S. And then potassium nitrate is still a nitrate. Nitrates are soluble, so we're going to put another aqueous. So this tells us what's going on. So when I look at this, I know I have two things that are dissolved in water, and then at the end I've got a solid and I've got another product that is also dissolved in water. So from here, we could also write what's called the complete ionic, which shows all of the pieces. Okay, so the molecular is keeping them in their compounds. I know these aren't technically molecules because they're ionic compounds, but we call it molecular because it's showing them as if they were in full chemical formulas. Okay, complete ionic is going to show all the components. So we're breaking everything up that can be broken up. So silver nitrate's aqueous, so it's not actually together as silver nitrate. It's split into its silver and nitrate ions. Potassium chloride isn't actually a solid, it's aqueous, so it's split into its potassium and chloride ions. Silver chloride's a solid, so it's going to stay bonded, connected together. So we leave that together because it's a solid. And then potassium nitrate, since it's aqueous, it's going to be dissolved in water, so it's not actually going to be connected. It's going to be split apart into its potassium and its nitrate ions. So we get from molecular to complete ionic based on those solubility rules. And sometimes it helps to visualize what this might look like in lab. When you dissolve silver nitrate and potassium chloride in water, they're going to completely dissolve. When you dissolve potassium nitrate in water, it's going to completely dissolve. When an ionic compound dissolves, it's breaking apart into its two ions. Now to get to the net ionic leaves out the spectator ions. So if they're not actually doing anything, if they're just floating around in solution, they always stay as ions from the beginning to the end, we call them spectator ions. So if we look at our complete ionic, our nitrate shows up in it as an ion on both sides. While when we write the molecular, we say it changes partners, it doesn't actually, because it stays aqueous in both situations. So it always stays as an ion, so we can cross out our nitrate ions. We're not actually going to cross them out. You could if you were writing this on paper. But we can cross out our nitrate ions. Potassium's the same way. Our potassium stays as an ion both in our reactants and our products because it's always in an aqueous compound, so we can cross out our potassium ions as well. That leaves us with our silver ion and our chloride ion forming our silver chloride. So our net ionic leaves out the spectator, it's only showing what makes the solid product. So there's another way if you didn't want to write out the complete ionic. You could look at your molecular and say, well, silver chloride is my solid, so that's the only thing that's actually changing any bonds. What are the two things that make up my silver chloride? Silver and chlorine. Therefore, I have to have silver and chloride ions as my reactants, and then my silver chloride as my product, as a solid. Net ionic equations are important when we're thinking about precipitation reactions because we really don't care about everything else. If we were doing this in lab, if we were isolating the silver chloride, we'd probably filter out the spectator ions with the water, and they don't really do anything. So that's the point of using a net ionic equation when we're looking at a precipitation reaction, is we're isolating our representation down to just what's essential, just what's going on in the actual reaction. So the only things that are actually changing their bonds.